My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and very good morning to all those who are watching this program live from USA. So today it's our 240th International Physics webinar. We are going to welcome you all to a joint session between our Department of Physics, Pabna, University of Science and Technology, and the Department of Physics, University of Minnesota, Duluth, USA. And we have with us here today Dr. Vitaly Vanchurin, Associate Professor, Department of Physics, University of Minnesota, Duluth. He has already connected with us, so I'd like to welcome our speaker. So good morning, sir, and good evening to you, and thanks for accepting our invitation.
Great,
So
thank
before
you.
going to you, I'd like to introduce you, our student. So dear viewers and students, I think you have already come to know the title of the today's International Physics webinar, and the title is Thermodynamics of Learning, from the machine learning to physics and biology. And our speaker is Dr. Vitaly Vanchurin, Associate Professor, Department of Physics, University of Minnesota, Duluth. And we can see he has completed his PhD degree in physics from Tufts Institute of Cosmology, and his master's degree from the Graduate School of Arts and Sciences, so from Suffolk University, USA. He completed his bachelor degree in maths and physics. And you can see he started his professional career as a research assistant at Tufts University, and then he joined as a postdoctoral researcher at University of Munich, and then he moved to Stanford as a postdoctoral researcher, and then he joined as a research associate there, and finally he joined as an assistant professor at the University of Minnesota in 2012. And he's also currently working there as an associate professor. So I think you will enjoy this session. So thanks for your patience. So it's your turn, sir. You can start your session.
Great, thank you. So when I scroll down the slides, I have to do it in a separate window. Is that how it works? I just want to check. Okay, it's fine. Well, thank you for the introduction. There is, as you see from the slide, there is one little addition to my CV. I'm currently in the transferring from the University of Minnesota Duluth in a transition to the National Institute of Health, and that is very much related to the things that I'm recently interested in, and this is something that you will see by the end of the talk. You'll see why I do have that made this transition. It has to do with the application of the theory of learning that I first tried to develop in context of physics, but later it became apparent that it has a wider range of applications. So let me now proceed with the talk. So I'll try to go slower, but if at any point you see that something doesn't quite make sense, don't wait until the end of the talk and just ask me a question right away. Okay, so so what's the idea? The idea is due to Wheeler, the original idea. So he said that, it may be that everything that we see around us, he meant mostly physical objects, have information theoretic origin in it, meaning that everything is information, and that is kind of a doctrine that he proposed called it from bit. So it was a bold idea at that time, but I don't think it was taken very seriously. And but over the years, many different interpretation of what this might mean, of how this might be useful, was put forward. And I think now more and more people are trying to study the possibility that the physical laws, and as I will argue, even maybe biological laws at the end come from some information origin. So I start with a Venn diagram just to illustrate kind of where we are. So you have information here, and that information kind of describes all of the possible computer science originated theories. So here I've listed a cellular automata as a CA. I also listed here the quantum computing, and those two are probably the most popular approaches that people take. However, there are others, and so the other approaches that there are involve machine learning. And so this is the newer twist that we get on the story of eat from bit. Nevertheless, this talk is about that. Now, I don't know if you can see the pointer, and it would be nice if I could get a pointer. Can somebody suggest me how?
No, you can't see your pointer. I think you
Because
can add your laser pointer.
how do I edit?
So you can click the right cursor. Maybe
Okay.
you'll get option.
Yeah, so all that I see is the live stream, and then
No, in that original file, not here. So you should go your.
I see. I have to switch back and forth.
No,
Okay, fine.
no. Just minimize it, and you can go
Okay,
your
got it.
PowerPoint or this file, and I think you will find that option.
Okay, so yeah, I don't see that option anywhere. Yeah.
Or
Yeah, I don't see. Okay.
yeah,
So,
now you can see your mouse.
oh, you can see the cursor. Okay,
Yeah.
good.
Yeah.
Because all right, fine. Then I'll just proceed with this cursor. Okay, fine. So we got so the idea is to be able to start or with information theory and somehow derive the physics out of it. Now, the more another idea that can go with it is maybe not just physics, but you can also try to derive more than just physics, maybe more complicated, more complex phenomena that are usually associated with biology. And I got to note that this neural network proposal of using information theory to derive physics actually fits pretty well with an attempt of also unify it with biology, because after all, the artificial neural networks we use in machine learning came from or inspired by the biological neural networks. But for now, it's just words. Let me just point out on this Venn diagram that this place here, which I don't know if you can see or not, this talk is on interface mostly between information and physics, but there can be other. There are two other projects that are currently underway that I'll mention are actually in the interface of information and biology and physics and biology, which is why I'm currently affiliated with the National Institute of Health, where I work on those projects. Okay, so let's continue. So far there are 4 references that I can cite here that indicate of what was done, and those 4 references are kind of split into halves. And one is a pure attempt of taking machine learning techniques and trying to derive gravity, and this is the upper trajectory that you see here. And the lower trajectory is the opposite. Is okay, once you've identified the connection between machine learning and physics, maybe you can already take some known physical theories, physical results, physical phenomena, and associate them with something in machine learning, so kind of help to develop new algorithms. So, and these two directions, they kind of go together, and every time you uncover some connection from left to right, it also shows you that there is actually a connection from right to left. Okay, so now to formulate more specific with the setup of the problem, and in this talk, I will mostly talk about thermodynamics as a link that as a technique, physics techniques, but it also a link that links theory of neural networks to physics and biology. So at the beginning, let's just take a bigger approach on this and see what this not it from it, but in this case AI from it might be. So right, so there'll be two: it from AI and AI from it. So let's start with AI from it, meaning we would like to use physics, or what we learn from physics, to understand how neural networks in a computer work and function. Now, the biggest complication in machine learning is that there isn't really a good theoretical understanding how it works. And the main complication is because the number of parameters that typically go in a typical neural network are very large. And the bigger network, the larger it is. And so the analytical methods that you might have used otherwise wouldn't work. Now, this situation is very familiar to us, to physicists, because this is exactly what we have in physics. When we are dealing with a system with a very few degrees of freedom, we know how to solve it. We know how to set up differential equations and study for the solutions of how systems evolve. Now, when the number of degrees of freedom becomes larger and larger, those methods fail. The standard method fails, so you cannot really keep track of every singular molecule. You want to use some kind of methods, coarse grain methods, where instead of following individual degrees of freedom, you follow their common properties. And so the idea is thermodynamics. Thermodynamics is a tool that allows us to replace all those microscopic degrees of freedom with some macroscopic parameters like temperature, pressure, and see how those evolve. Now, what is thermodynamics? Thermodynamics is as a tool, as I said. It's a phenomenological tool. You can, for certain system, derive it from the microscopic description, and that is usually goes through statistical mechanics. So basically, you formulate probability distributions of, say, molecules, and then study how they evolve and derive how the macroscopic parameters like temperature, pressure would change. So it's phenomenological because you can only do that for very simple systems, but then you kind of understand how whether the general principle behind this, how they work, and then you generalize it to more complicated system, to the systems that you may not be able to even conduct your calculations analytically, but nevertheless is possible to do at the level of phenomenology. So the original proposal is that, okay, so let's take the neural network, large enough, so there are many degrees of freedom. In fact, for thermodynamic description, it is better to have more degrees of freedom. The more molecules there are, the better the thermodynamic description is. And so in the case of neural networks, the more neurons there are, the better your description would be. So you start with the neural network, large one, and then instead of following evolution of individual neurons, you just say, let's consider ensemble probability distribution over different values. And the idea is from that to derive thermodynamics. Now, there's no guarantee that this thermodynamics will be the same as the thermodynamics that you derive from classical mechanics, from standard classical physics. But it is a way that we can try to go and see what happens. So that's kind of the basic idea. So now, what are the neural networks? And here I'll have two slides, and one is which would be more familiar to people with computer science background studying machine learning, but it will be rephrased in a different language. And another one is more familiar for the physicists who are familiar with problems of general relativity and quantum gravity, or how to unify the two. But the two are connected, as I'll argue, and so the reason I introduced those two perspectives is kind of to assist people which have already some background in this with connecting the dots. Okay, so what is a neural network? It's a dynamical system where there are certain degrees of freedom that change according to certain laws. And one type of degrees of freedom is a state vector of neurons. This is the first one. Okay, and the state vector of neurons is important. That is it is non-trainable. You do not really train it. It propagates through the network. But the trainable parameters that I'll discuss later are the ones that affect how it propagates. So each neuron kind of associated with a single real number. You can complicate it, you can make it complex, but that wouldn't really change the setup much. Okay, so yes, so you have that. So you have a state of neurons. Then the neurons are typically divided into two types of neurons. I don't know why this highlighting works, but okay, let's just go with it. The input and output neurons. So then there are two types of them, and the input ones can be on one side and the output can be on the other side. But what's important that one should imagine that all those input and output neurons, you can imagine that all of them are kind of on the boundary, reside on the boundary. And then you have a training data set. So this is a data set which you supply to your system. And this is a data set at the boundaries where the input neurons and output neurons are. You supply this training data set, and the network tries to adjust its parameters. So this is the training data set now. And then network tries to adjust its parameters so that the parameters are the weight matrix and the bias vector. So those are the two types of parameters. It tries to adjust it so that the loss function is minimized. So that's kind of the setup. And so this trainable parameters W and B propagate depending and change depending on the loss function, but non-trainable variables change according to the activation function. So this is the setup. So there is like kind of the 7 main ingredients that you have. And those 7 ingredients determine or define the neural network from the perspective of the machine learning. Now, in the physics perspective, what is important is the loss function. So this is the loss function and there are really 2 types of loss function. It wasn't obvious here, but it should be obvious here that there are 2 types of loss functions. And these 2 functions are either defined on the boundary or on the bulk. So for example, you can propagate your signal from left to right and then see the mismatch in the values of neurons on the output boundary. This is how usually the recognition works, that speech recognition or recognition of images. In the input layer, you would put in the picture of the dog and a cat, and in the output layer, there would be a bit that will tell you whether it's a dog or a cat. And the mismatch, how many times or how big of a deviation from the correct answer you get, is your loss function, is your error. But that is the loss function that is located on the boundary, and it defines kind of a mismatch in the boundary conditions that it was supplied with the system. However, the bulk equation are satisfied exactly. So this activation function propagation goes as defined. And that is great for supervised learning, which is the example that I gave you with pictures of cats and dogs. Now, it doesn't really work with unsupervised learning, but there is another possibility of defining a bulk loss where you do not specify the loss at the boundaries. You specify a loss for each neuron in the bulk, okay? And you kind of demand the neuron to have least entropy, least changing state, have a smallest mismatch in the equations of motion. So now your equation of motion are not satisfied exactly, and so there is this mismatch, and that before they were satisfied exactly. However, contrary to the bulk loss, now your bulk boundary condition are satisfied exactly. So again, if you took the error from the boundaries and put it in the bulk, and you can now use that for both supervised and non-supervised learning. Now, to physicists, this quantity that is called the loss function should be associated with energy, with a Hamiltonian. And so that is why I use the notation H here. It will play a role of a Hamiltonian for most of the parts. And when we develop the thermodynamic theory of learning, this is where it will stand. Okay, so fine. So we have these two types of loss functions. One is at the boundary, one is in the bulk. So let's just put real data. Let's train a network and see how those two loss functions change. So this is an example of a simulation where the data were handwritten images of numbers from 0 to 9. And then the point for the network, the aim of the network, is to minimize the loss. So if it's a 0, that it should associated with a 0. If it's a 1, it should associate it with a 1, etc. And as the training progresses, and this is a very simple network, so it's not supposed to learn fast. It is just supposed to show how the loss functions change. And so as the learning progresses, the loss functions decay, both boundary and bulk. And you can notice there is one difference. The boundary loss makes sudden jumps when the bulk loss is more or less smooth. So let me just plot now not versus the time or epochs, but versus each other. So if I plot these functions versus each other, then I see this effect. So basically, the learning takes place, and then all of a sudden there is a jump. And then again, there is no learning, and then there is a jump. There is no learning, and then there is a jump. A jump in the boundary loss. So, but throughout this evolution, the bulk loss seems to changing all the time. So I have this picture of the Eureka effect, which I think illustrates this well. So you can kind of try to solve a problem, and you sit down and think about it, and you still don't get the answer. And but then eventually you figure out the answer, and all of a sudden there is a sudden jump in the loss function. You know how things work. Now, although it happens suddenly, the neurons inside your brain are being adjusted all the time. So the actual loss inside the bulk loss is continuously, monotonically decreasing function, and there are not many sudden jumps there. You also see this effect when you study physics. Say you are reading a chapter, it makes no sense, you cannot solve problems, so your loss function is very large. Now, all of a sudden, you figure out how things work, and then suddenly the effect takes place. You have this sometimes called aha moment, and then your grade is greatly improved because you suddenly figure out how certain things work. So this illustrates the aha effect, illustrates the difference between the boundary of what your answers to the quiz questions are to what actually happening inside the network. Okay, so fine. We've associated the quantity, which is a loss function, and that that is really all you need to go on and develop a thermodynamic approach. So let me take through it so that so that you can understand the logic. So what is given to a neural network? Given is boundary data. So in the previous example of the simulation, what was given a set of written images of numbers. How can be pictures of cats and dogs. It can be anything at all, and it doesn't need not be something that it has applied nature. It can be just state of the boundary condition of any physical system. So we take a physical system, there are certain state of the boundary conditions, and those boundary conditions change over time, and by doing that, they form a probability distribution. This is probability distribution on the boundary, which I denote with the PD. Now what you can do, you can extend this probability distribution to the bulk using equation of motion in the bulk, using how the neurons activation function propagates through the bulk, and you get a probability distribution P0. Now, it is a legitimate probability distribution, but analytically, it's very hard to work with because it has a delta function in it. What physicists usually do, and that is the key idea, is you can simplify that by replacing this delta function with a sharp exponential. And then when you do that, you of course change your model, you change your system. However, in the limit, when the number of neurons, number of degrees of freedom very large, these two distributions are indistinguishable. In physics context, the first one equation now is usually called the microcanonical ensemble, when the second one is called the canonical ensemble. And so it really helps a lot when you're trying to do the calculations. And the calculations follow as usual, so I'll go through this quickly, but the idea, again, you will see this H appearing everywhere because this is your loss function. The main tool in developing thermodynamics is forming the partition function, where you take an integral of this exponent over the entire space, phase space, so here over all axes. And then you obtain a partition function, and that partition function kind of tells you everything about all of the thermodynamic properties of the system. Now, the challenge is to take this integral. And this integration can be easy or hard depending on what your loss function is. Now, in certain cases, for example, for the hyperbolic tangent activation function, you can really approximate the exponent with the quadratic function, and then this becomes a Gaussian integral, which you can easily take, and this is the answer. Now, inside this answer, there are some parameters that are like G, and this G actually depends on the weight matrix and the state of the bias spectrum. I'll call it Laplacian matrix because that is the role that it plays in the canonical partition functions that we usually deal with in physics. So when the loss function is quadratic, things are easy, or if it's well approximated by quadratic functions, it's easy. You can just calculate it, you can get the answer. And so as you see, everything, as I told you, that everything about thermodynamic properties, all the thermodynamic properties are in Z, and Z depends only on this Laplacian. So if you know the Laplacian, you really know how the system will behave. You can also flip things around. If you say, I want the system to behave in a certain way, then let me choose the Laplacian that does that. So if I want the system to find the solution faster, to learn faster, then what kind of G should there be? And then you can start with the G, which is already a good learner. And as I'll argue, there are Gs that are good and there are Gs that are bad. And so you should always start with a good one. So now let's get to this G operator. It is a matrix. So the best way to study a matrix is through its spectrum of its eigenvalues. So here I plot logarithms of the eigenvalues for a typical shallow network, which has only one hidden layer. And this is how this G changes as learning progresses. So now we're kind of diving into the network that undergoes learning evolutions. We've specified, we only constrained the network to be shallow, but other than that, it tries to learn the boundary data, which in this case are the same handwritten images of numbers. And you may notice that there's one weird thing about this spectrum. It is very symmetric around 0. Now it is a logarithm of eigenvalues, but nevertheless, you see it's very symmetric. So the shallow network is like that. Now, this is why shallow network is not a very good learner. It can learn. It will take you longer, as I will argue, but nevertheless, this is the real reason for that. It has the properties of the weight matrix that are translated into the properties of this Laplacian matrix as such that distribution is symmetric. So now for the deep neural network, things are different. So now it is the same simulation with the same number of degrees of freedom, so trainable parameters, but now it's deep, and you see that it's not symmetric. So it has skewness, which is not 0. And that's very important. So now I will skip through this, but this is just for you to see that I am not lying. If you have Z, you can calculate everything. You can calculate average loss, you can calculate free energy, you can calculate entropy, complexity, and etc. So like Z is, the partition function is the key. So you have it, you know the system. And then there are two ways to obtain Z. Either you start from the microscopic description and do that integral that I said, usually hard to do. Or you just say, well, forget the microscopic side. Let me just reconstruct the Z from the experiment. Okay, so so I showed you how the spectrum of G evolves. Now here I introduced the loss function, and then also there is network complexity. So just to show you how things evolve with time. So the complexity or the rank of weight matrix decreases with time, and so kind of the system becomes has a fewer and fewer parameters that are really needed to solve the problem. So it really compresses itself, and this is good because it frees the parameters to do something else. So if later on some new data come in and your neural network must be trained for that data as well, it has resources for that because it kind of compressed itself. And it compresses itself not because of the algorithm, but because of how thermodynamics works. Okay, now let me just now formulate the laws of learning, which are similar to the laws of thermodynamics, but kind of often work in the opposite direction. So if you usually start with a thermodynamic system, you know that eventually the entropy will grow. It will be more and more, state will be more and more random. In this case, this is not how neural networks work. They do the opposite. They're actually trying to decrease the randomness. They want to make the network be more predictable. And so you can follow it computationally and see that not only average loss decreases, but the temperature-like parameter, which was this inverse of beta that appeared in the partition function Z, so that parameter also decreases. So the temperature is decreasing, and then the entropy is decreasing. And so the system isn't behaving, the learning system isn't really behaving how would classical Hamiltonian system would behave. And so I call it the second law of learning, although it's similar, but the difference is that if the learning dynamics dominates the dynamics of your system, then this is what's happening. The entropy must decrease. You also have the first law of learning, which is similar to the first law of thermodynamics, that relates tells you how the system would behave, let's say, in an equilibrium. So in equilibrium, you would have free energy, change in the free energy equal to 0 in a canonical equilibrium. And then this will tell you that any increment in the loss function should be equal to the increments in the entropy and the complexity, or just the total entropy. If you have other parameters that external parameters of the system that can control it, then those parameters will appear in this first law as well. And here is an illustration how the complexity and loss functions kind of behave. Both of them are decreasing functions with time. Now, let me go back to the question of, all right, so I have this thermodynamic description. How can I develop the neural network that learns better? So this kind of will be one of the application of thermodynamic approach, and the other application will be is in the opposite direction, taking this thermodynamics of learning and applying to physics or biology. So we have a theory of thermodynamic theory of learning. And so first, let's see how we can improve algorithm, and then let's see how we can model the universe. So the key idea here is to use the principle of minimal entropy destructions. Generally, can be more generally defined as the principle of stationary entropy production, where stationarity can be either minimized or minimized. It's very much related to Occam's razor principle, meaning that you really want to have a system that compresses the data, compresses your network, so that there are more and more data is available. And so you're trying to choose, the system is trying to choose a path, optimal learning path, where you destroy the entropy, but in a minimal possible way. You always destroy the entropy, but you want to have it in a minimal possible way. So there are more and more entropy in the trainable variables available for you to perform learning. And so here, without going into details, I just show you how those eigenvalues of the Laplacian matrix evolve. And this is what happens when the temperature changes. So when you go from blue to red, the temperature is decreasing. So beta is increasing, but the temperature is decreasing. And so first, you roll to the left and to the right. And then, and the more you can roll to the left, more eigenvalues can roll to the left, and further away they can get, the more compressed the system will be, and so the better learner it will be. However, as that happens, the temperature decreases as they roll to the left, and so this bar is always being raised to the left side, and so eventually it stops, and so the eigenvalues just get stuck someplace here. But the further they can run to the left, the better it is for learning. And so you see this picture is not symmetric. So it is to the advantage of a neural network to have a distribution of eigenvalues of this G matrix, Laplacian matrix, such that this isn't symmetric. And so we can kind of say, all right, so let's now look at the neural architectures and see which architectures give you the desired asymmetry in the distribution of eigenvalues. And we see that for shallow, it's very symmetric. It's not good. But for the deep, it is not shallow. And so you see this eigenvalues run to the left. Those are the same eigenvalues that run here. And so you can actually do the calculations and so show analytically why the shallow networks are such that the skewness is actually 0, and the deep networks is such that the skewness is large, and we want it to be large so that Laplacian of the free energy, again, something that has to be explained better, but for the lack of time, I'll just go with it. And then that would imply that the entropy destruction is smaller, and so you have more resources to continue be a more efficient learner. So then the architecture is really mapped into the gene, and before you start learning, you can really set already your system such that it has that. So this is one application of thermodynamics to deep learning, to developing algorithms. There are others that I don't have time to talk about, but right away, in the beginning of your simulations, you can evaluate this G matrix and say, okay, no, it's not good because it doesn't have the desired properties. Its spectrum doesn't have the desired properties, or otherwise it does. Okay, but now let's take this thermodynamic approach and see whether it is useful for physics. So many people look at that picture as something which inspires possible connections between the universe and our biological neural networks. Now, there might be relations between these two pictures. So let me just tell you that on the left side, you see a biological neural net, not the artificial one. And on the right-hand side, you have the cosmic web of the large-scale structure. They do look similar, but for now, I don't have proof that the mechanisms behind them are the same. And so for me, really, the starting point will not be that, but will be the thermodynamics that we just developed. So let's take a thermodynamics and let's see what are the other possible limits of large neural networks that we can analyze. Can we claim that all observable phenomena on the fundamental level of physical phenomena, on the fundamental level, I actually resemble the computational evolution of neural networks. So far we discussed all the thermodynamics, and not real the physical thermodynamics, but the dynamics of learning. And so that was kind of the main message in the preceding slides. Now, you can actually go deeper than that. And I will, out of this list, I will talk more about quantum mechanics and general relativity. But really, there are papers and there are calculations that show that now taking different limits of how neural networks behave, you can obtain approximate equations that resemble the known equations we have in physics. So let's start with this quantum mechanics. That was the hardest one, but it wasn't. So it was the hardest one because right away you do not get quantum mechanics. So if you just study the dynamics of trainable variables and see how they evolve near equilibrium, you obtain something very close to quantum mechanics, but not exactly that. However, later, if you say, in addition to evolution of trainable variables, I want the neural network to have additional feature of additional algorithm that tells you that the number of neurons must not be constant. It should be allowed to vary. Then you obtain quantum mechanics, as I'll show in the next couple of slides. You can also study the behavior a little bit away from the equilibrium, and then you obtain the classical equations of motion. You can obtain self-organized critical states that are very important. Many people believe that this is how complexity of nature arises. Now, it turns out in neural network, it is a generic feature. So there are certain variables in the neural network that experience scalar invariant fluctuations. Those are actually the variables that are trainable variables, but they were not trained well. So this is the ones that are still in the progress of being trained, and they form a critical behavior. So if you see fractals are about those variables. Variables that are trying to get trained but not quite there yet. Now, the hardest out of all the two remaining ones are the hardest one is the general relativity and observers. So again, all of those are phenomena that we observe in physics, and depending on who you ask, different people will tell that the one of them is more fundamental than the other. The approach here is that all these phenomena are not fundamental. They're all emergent from the underlying dynamics of neural networks. So they're all limits, like thermodynamics, which is universally believed to be an emergent phenomena. We also think that quantum mechanics is emergent, classical mechanics, self-organized criticality, and even general relativity, and I'll talk about this a little bit, is something that not fundamental, it emerges. The space and time isn't fundamental, it also emerges from the learning dynamics. Now, I'll mention a little bit on this because this is still work in progress. Progress with biologists. So here I'm kind of relying on the experts to help identify the biological phenomena, okay, the minimal set of the biological phenomena that needs to be explained, and then see if those phenomena can be explained through through learning. Now, it can be learning as the one we see in the computer, or learning that we see in the computer with additional ingredients, additional algorithms. Those algorithms that we haven't really applied to artificial neural networks yet, but the nature had. Okay, so in the last 3 slides, I'll just go through quantum mechanics, general relativity, and a little bit on observers, and that will be it. So emergent quantumness, or viewing quantum mechanics as not as an emergent phenomena, is a relatively new field. It grew out of the previous program of the pilot wave function, but more recently, I think the approach is that, well, maybe it is an emergent. It's not just that you have to supply the Schrödinger equation with additional equation for the pilot wave function. You just derive it from as a probabilistic theory in a certain limit. And the claim here is that it's true. You can derive it using the same principle of stationary entropy production that gave us confidence that the deep learning is good. So you take the same principle and you form action that, upon minimization, tells you what the best trajectories the system must take. However, you do not obtain the Schrödinger equation. You get the Mondelong equation, which is very similar to Schrödinger, but it is not the same. Now, to get it to be the same, you have to consider a grand canonical ensemble of neurons, and then if this number of neurons is not observable directly, so you can imagine you have a neural network, and then it undergoes learning evolution, but some neurons becomes active and unactive. They activate, deactivate, and if that happens all the time, you don't really know how many neurons are active at any given time. Then it might be that this network will have emergent quantums. It will behave as a quantum system with all of the quantum advantages that you can get from that. So that's one. The other one is a gravity. It's a little bit trickier here. Really, the tricky part. So if you notice here, you study the entropy production of the trainable variables. For the gravity, you need to study the entropy production of non-trainable variables, the states of neurons. Once again, you apply the principle of the stationary entropy production and study the dynamics. And you can study it only in, again, very specific limits. So you haven't, we're not able to analyze all possible limits. And in those limits, you see that there's some kind of relativity emerges. So in particular, if there's non-trainable variables form subsystems, and then kind of each subsystem passes through the same network, but have minimal interactions with each other, then these subsystems actually form the space-time, d plus one dimensional space-time, which can be curved. And this d is the number of non-interacting subsystems. So in our case, it would be 3 or more. There are some hidden dimensions. But the main point that you are really using the same tool of the entropy production as we used in the quantum mechanics. So in one case, you pay attention to the entropy production of the non-trainable variables, and the other one, trainable variables. So perhaps those are just dual description of one another. And if you can just equate those to entropy production, then you can analyze the same system from the point of view of the non-trainable variables of trainable variables. or from the boundary and bulk, or from the quantum and gravitation, or from equilibrium and not equilibrium. And so those mappings allows you to kind of carry on calculations in one setup and then translate it into the other setup. So that has relations to something that is nonholography that I've mentioned here. In the last minute or so, I'll just mention that this is a work in progress. We are almost done. I'm not able to actually report all the answers yet, so it's a large collaboration here. We have 2 biologists and 2 physicists working together, trying to take all the biological phenomena and try to explain them through learning. And there's some progress being made, so I've mentioned here a few things. So you can identify the biological loss function. It is related to what is biologists call fitness. The relation isn't straightforward, but now you can also formulate something like biological temperature, which is what I called one over beta in the previous slides, right? Once you have loss function, you can form a canonical ensemble, and so then you can formulate something called a biological temperature, and then you can take all this thermodynamic approach and define biological potentials, study phase transitions, how things happen, and they are related to the major transition in evolution, if you're familiar with those. You can also apply this logic of renormalization group, where learning does not happen only at a given scale, it happens on all scales, but at different scales, it manifests through different biological phenomena. So this is just a quick overview of the direction that we are heading, but presumably very shortly we'll release a paper or 2 which clarifies all of those aspects. So let me summarize now. So there are really 2 directions that I'm advocating here and proposing, and we are working hard in both directions with the computer scientists, biologists, physicists. And so one direction is really take AI or artificial intelligence or machine learning as your fundamental framework, and then from that framework try to derive certain aspects, and that can be useful to derive not just thermodynamics of learning, but also to propose things like artificial quantum computer that I haven't talked about, and to design optimal architecture. So it helps you to improve your knowledge of artificial intelligence. So this is people what in artificial intelligence community are complaining. We have deep neural networks, they work, we don't know why. So this is a proposal of how one can proceed to try to understand, maybe not how everything works, but how little pieces of it fit together. And then there is number 2 direction, right? So it's eat from AI. So how can you derive the universe, the observable universe, everything we see without us, around us, from artificial intelligence? So in this, so number 1 is kind of guaranteed to work because all you're just doing is mathematics, that using the tools that physicists are familiar with. In number 2 is a very ambitious project. It's saying that everything is a neural network, but it has different limits, where at some point this neural network near equilibrium, it behaves as a quantum mechanical system. In other limits, it behaves as general relativity. In the third limits, it can have some self-organized critical states, or biological evolution and phase transitions can take place. So those are the 2 directions that I've kind of summarized here, and I think I will end here.
Okay, thank you, sir.
Thank you.
Yeah, thanks for your wonderful presentation. So we have got 2 questions in comment section. So if you allow, we can start our discussion session.
Sure.
First question is very simple one. What is the loss function?
Yeah, so loss function is mismatch in what your neural network predicted and what the ideal neural network should have predicted. So in the case of the handwritten images, if your input layer you had somebody wrote a 0, then at the output layer there should be bit which is assigned to 0. Now, a neural network will not always have that, and sometimes it will make mistakes. So mismatch by how much you're different from your how much your prediction differs from what you want the state to be is the loss function. So it's error, cost function. So it goes by different name: loss function, cost function, energy in context of physics, etc.
Okay, sir, thank you. We have another question. So, what are the unsolved problems in non-equilibrium thermodynamics about the system out of equilibrium? What can be
Very
done
good
to solve
question.
it?
Very good question. Yeah. So it's actually the reason it's good because the non-equilibrium thermodynamics is really poorly understood. People don't disagree of what this really means, what it is. Now here, what I would call non-equilibrium dynamics is the dynamics which doesn't follow the laws of the conventional thermodynamics, and in this case, learning thermodynamics is the non-equilibrium thermodynamics. It is a mathematical framework that allows you to study a system which do not behave as a thermodynamic system. So it's so this is a step in that direction. But generically, there is no general agreed framework of working in context of non-equilibrium thermodynamics. And so this can be considered as one of the proposals for that. Yeah.
Okay, sir, thank you. We have another question. So, what is the thermodynamics in black holes and how does it work?
Yeah. So now black holes arise as a solution of the general relativity. And so here I've had only one slide showing that the neural networks can exhibit a behavior similar to general relativity. Now, if that's correct, then the black holes will form, and so in these black holes, around them at least, the evolution will be resembled by the laws of general relativity. However, deep inside the black hole, maybe right at the horizon or further, closer to the singularity, the system would not behave as predicted by general relativity, because in this setup, the space type is emergent. It isn't like fundamental. It's not like you have three-dimensional space and then you place some particles on it. The whole system emerges through learning. And so to answer your question, you will see deviations from black holes solutions. And so the black holes would not be the right description of the dynamics. And that gets kind of so that's one answer. The second answer is related to the holography and an attempt to actually study the evolution of gravitational system from the quantum mechanical perspective. So this is something I mentioned. So although we may not have a correct gravitational description of what happens inside the black hole, you may have a quantum mechanical description that will tell you how the black hole should evolve. Again, this is a very good question, but I think it's too early to say what's new the neural network model brings to the problem of black holes and information paradox.
Thank you. So, we have another question. So, does the laws of thermodynamics apply to dark energy?
Another,
And
go ahead.
will thermodynamics help us understand the dark energy?
Yeah, very good question. So that actually, I think, may be actually simpler to understand in context of neural networks. Again, laws of thermodynamics per se would not shed light on the dark energy problem, but when you study the evolution of neural networks and model them with JAR, I think getting a cosmological constant there is a generic feature, not something that you have to put in by hand. Now, again, this is I'm saying it with some hesitation because there's certain calculations that we're now doing that will confirm that. But I think to answer the question as it was formulated, the thermodynamics itself doesn't shed light on the problem of dark energy, but the thermodynamics of learning might shed light.
So thank you. We have another question. So just curious, how does thermodynamics explain why there is acceleration in the expansion of the universe?
Right. So that follows from general relativity, right? So if you can derive general relativity, then again, I mean, if you derive general relativity, then you have dark cosmological constant, and that gives you acceleration. So this is kind of related to the previous question. Can you get dark energy or cosmological constant from neural network setup? I think you can. And so basically the answer would be the same as the previous question. I think it's easier. I think you can, but calculations need to be done to show that. Now, still the first step before we get there is actually not to have a phenomenological derivation of general relativity, but a microscopic. So for now, general relativity was derived phenomenologically. We see where the metric comes from. We see, why the space-time is emergent. We say, okay, what kind of dynamics can this metric obey? And then one of the answers is general relativity, but there are other answers. So we should better first understand why is a general relativity a better choice. When we answer that, then acceleration of the universe is just the result of solving Einstein equations with the cosmological constant.
So thank you. We have another question. So how neural network could be helpful in particle and the neutrino physics?
Yeah, good question. So now, if a neural network model of the universe is correct, then the fundamental objects are not particles. Okay. Now, fundamental objects are maybe closer to strings, but not really strings either. They are neurons. So, and those neurons would form together complicated subnetworks that would behave as particles. And there would be some networks that behave as electron, quarks, etc. Some of them would behave like neutrinos, and understanding which architectures give rise to which particles is also another work in progress. It's a missing step of deriving not just quantum mechanics, but deriving the standard model. Now, what will probably happen is that the standard model would not be a preferred choice. It will be just one of the choices. So you have a neural network, it evolves, it tries to find some stable states, it learns its environment, and then one of the solutions to this learning evolution is the standard model that we observe with neutrinos and quarks and electrons, etc. But then it will be others. So I think the correct way is to imagine as a landscape of possible solutions, with our high energy physics being only one of the choices of the many. So then you would not be able to really derive neutrinos, why this is a preferred choice. There could have been anything else, but at least you would be able to show that this is a consistent solution. In a way, it is similar to the string theory landscape approach, although I think here you can, but in both situations, calculations need to be done to show why either strings give us the standard model or neurons give you the standard model.
Sir, thank you. Now we have another question. Can laws of thermodynamics be broken?
Oh, absolutely.
Can it happen in future? And what will happen if a laws of thermodynamics of physics etc. is broken? And will they revise the laws?
Oh, many
what
questions.
Will they do?
Let's take one at a time. And all very good questions, actually.
Yes.
Okay, so let me just take one. Now, I'll read it myself. So yeah, so the laws of thermodynamics can definitely be broken. Okay, so laws of thermodynamics really apply to only equilibrium states. when you are in equilibrium. And the further you get from the equilibrium, or the smaller the number of neurons there are, or degrees of freedom, the further away you are from the thermodynamics. And that is true for the conventional thermodynamics, and it is true for the learning thermodynamics. There's no difference between the two. Now, however, it's very hard to set up a system with a very few degrees of freedom, okay, where you can see this broken thermodynamics. So one example of when the laws of thermodynamics are broken is when you have a broken ergodicity, when the system doesn't have time to explore all of the phase space and kind of form the canonical ensemble. So, and those things we observe. And that applies equally well for the laws of thermodynamics and of learning. Now, it can happen in the future. It did happen. It will happen in the future. It happened in the past. And so this is not a problem. Now, does it break physics? No, because physics is not just about thermodynamics. Thermodynamics is just one limit of physics, okay? And there are other limits. And I think there are, actually, if you want to kind of summarize all of the physics, there are three perfectly good limits. And they have some overlaps, but one is thermodynamic limit, one is quantum mechanical limit, and one is general relativity. So those are the three limits that you can study independently, and you can break one without breaking the other. Will they reverse the laws? That I wouldn't know what, but I think if I'm just guessing, the best reversal of the second law of thermodynamics is the one that I wrote down. The entropy isn't growing; it's decreasing because of learning. So that's a possibility. Okay, I tried.
Okay, sir. Yeah, thank you, sir. It was a big question, but you have answered it very well. So we have another question. So can machine learning techniques leads to a substantial progress in string theory?
Oh, absolutely, yeah. So this is it's useful for all branches, right? So basically, you're always dealing with some problems. You're often dealing with the problems where you can just not solve it analytically, and you have to employ numerical techniques. And so far, we had one technique in physics, which was numerical simulation, lattice field theory. Now here we have this additional tool. Now, some people are already applying it now and trying to solve problems that were not possible to solve before. And I think it's it's a promising direction. However, I think before we do that, it would be nice if we first understood how machine learning actually works, right? So if we understand them, then perhaps your success in making progress in string theory is bigger. That's one aspect of the question. The other aspect of the question, and I think I had this in one of the slides, is actually the learning dynamics of neural networks. In certain limit, produces chains of neurons, and their dynamics is similar to dynamics of strings. So in this case, you may have strings emerge from a neural network. Now, those will be simple strings because they would not be very generic. What's more generic are not the strings, but networks. So if you can have a simple network, which is just a chain of neurons, that would be like a relativistic string. But if you have networks, that the dynamics would be less of a stringy and perhaps more interesting.
Thank you, sir. This may be the last question.
Sure.
Okay, so what should be improved and created in the technologies of the future to learn and discover more advanced about thermodynamics?
Okay, what should we improve and create in technologies of the future to learn and discover more advanced about thermodynamics? Okay, so I think what thermodynamics is a phenomenological tool, and so this phenomenological tool must be tested in different limits, right? So the way there are two ways we can make progress with any phenomenological theory. Only two ways: it's bottom up and top down. So you can either try to cook up experiments which will test the behavior of, let's say, not so equilibrium thermodynamic systems, and that will tell us how to improve our description of the system. So then, it's experiment-driven advances in thermodynamics. And the other one is starting from the theory and seeing what kind of different limits you can get from the theory. And then if the theory gives you some new limit that we haven't talked about before, then this may enable us to describe things that we previously were not able to describe. So I'll give you one example that I think that we may be able to describe. So the biological evolution. So previously, there were no physical equations that one could write down and describe biological evolution using thermodynamics. So I think this is something that we can already do. We are kind of finishing up a paper on that. You formulate a thermodynamic laws, you write down an equation, and you show that, yes, that is the laws by which the biological evolution takes place. Okay, so here is an example of how the theory can explain the experiment, but also experiment or observation of biological evolution told us of what the theory should give.
Sir, thank you for your wonderful and exciting presentation and nice discussion session, sir. It was a great opportunity for our students and viewers to learn a lot of things about thermodynamics of learning. So, as our main aim of our program is to motivate our students, I think by your wonderful lecture, some of our students and viewers have already motivated. So, thanks again for giving us this opportunity, sir. And hopefully, in near future, we can arrange another webinar with you, sir. So, bye for today. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So, bye.
Thank you. Thank you so much. Bye-bye.
Have a nice day, sir.